All right, folks, I'm going to let one more question go by as our last few guests seat themselves. All right, everybody, we are ready to get started here. Welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today for our tour of the universe. How many of you were in a show earlier today? A few people. How many of you have seen one of our shows in here before? Okay, a few people. Okay, cool. This is one of my favorite shows to give because it's a little bit different than a lot of the other shows that we have throughout the day. Most of the shows that we do are largely pre-recorded movies, kind of, with a short section where I can update you on a particular astronomy topic. This show is different in that it is a completely live show, so I'm going to be our pilot as we fly through the universe today. We're going to start out at Earth, we're going to zoom out as far as we can out into space, and I'll take you safely home at the end of the show. And in order to do all of that, I do have to head all the way up the stairs to our pilot's booth, which is at the top of the room up there. So as I head up the stairs, I have a few quick housekeeping planetarium rules to go over. First of all, please no eating or drinking while you're in the planetarium today. And while you're following that first rule, the next rule should be pretty easy. We are still requiring our masks right now, so make sure to keep your mask on for the entire show. If you have a cell phone, a camera, a tablet, anything at all that could give off light or sound, both of those can be very distracting in here. And we don't want to accidentally run into a planet or something because I'm distracted. So make sure to keep those put away during the whole show. For your safety in this dark theater, we do highly recommend staying seated throughout the entire show. If you do find that you need to leave early for whatever reason, the exits are either side at the top of the stairs. And last but not least, this can create a very immersive experience. And while I do my best, I'm not a perfect pilot. So if at any point throughout the show, you feel any dizziness, any motion sensitivity, just close your eyes for a few seconds, and that will help your brain remember you're just sitting in a chair in a planetarium, not actually flying around in space. So without further ado, go ahead and sit back, relax. I'm going to move into our pilot's booth here and get us started. All right, so we are starting our tour of the universe today, relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And I always like to start out our tours at the International Space Station to give us a little bit of perspective on the incredible distances that we're going to cover today. Because today we're going to see how far our human influence has gone out in space. So we'll see things like how far have human beings traveled? How far have our spacecraft traveled? And how far has anything that we've sent into space gone so far? But the International Space Station, just a few hundred miles above the Earth, is as far as humans travel out into space right now. You can fit about 6 astronauts in it at any one time. And the longest any one particular astronaut has lived there was about a year. And folks have been living up there for about 20 years now. And they swap out usually every few months or so. They don't stay up there too long. But as we zoom away from the International Space Station, I'm going to bring up a yellow line so you can see where it's going around our planet. And they're traveling around us very quickly. It only takes about 90 minutes for the International Space Station to orbit us once. And we're not seeing too much detail on the Earth so far, but as we zoom away, we should start to see different features like clouds and weather patterns show up. And something very cool about this particular show as well is that I'm doing all of this with a free software called OpenSpace, which is a free open source planetarium software that uses all real data. So everything that you're going to see today is based on actual pictures or data of the places we're going to visit. So this is the real-time location of the ISS right now. It looks like it's maybe near Hawaii. I think that's Hawaii down there. And we're seeing what the clouds and the weather patterns were early this morning. But I'm not going to stick around the Earth too long, and I'm not going to stick around any particular place too long throughout the entire show because we have a lot of ground to cover. I mentioned at the beginning, we're going to start out at Earth and we're going to go as far out into space as we can. So we have a long way to go. But our next stop on our journey is going to be not our closest place where the humans are now, but how far humans have gone in the past. We're going to fly over to our closest natural neighbor, the moon. Now, sometimes this move goes kind of quickly, so if this makes you dizzy, just close your eyes for a second. There we go, and we're going to fly over to the moon. Now, the moon is as far as humans have traveled so far. It's our closest neighbor, but still, it's about 250,000 miles away from us, so still pretty far away. And when the Apollo astronauts came out here, it took them a couple days to get here because it is quite far away, even though it is our closest neighbor. And at the moon is where I like to introduce an idea that I'm going to be using throughout the rest of the show, since we're going to be covering some incredible distances today. We've already covered 250,000 miles. We're going to see distances of millions, billions, even trillions of miles and kilometers. So from here on out, I'm not going to use any of those terms to tell you about how far we've gone. Instead, we're going to imagine that we are traveling incredibly fast. We're going to imagine that we're traveling at the speed of light, the fastest speed we know of. And even faster than that with our OpenSpace magic that we have here. So for instance, if you were to fly to the moon from Earth, and if you were traveling at the speed of light, that fastest speed we know of, it would take you about 1.5 seconds to get to the Earth, from the Earth to the moon. So we say the Earth is 1.5 light seconds away from us. Or the same amount of time that took us to fly over here in open space roughly is how long light travels there as well in real life. And I'm going to zoom us away so we can start to see another line here I'm going to bring up. I'm going to bring up a blue line to show us the orbit of the moon, where the moon goes around the Earth. And anytime you see a line of any kind throughout the show, that's showing you the path that something is taking. So we can see the moon's orbit around the Earth, and then we're also seeing now the orbits of the planets in our solar system going around the sun. So that distance from the Earth to the moon, that's only about 1.5 light seconds, but even just zooming out here, we're now getting up to a few light minutes of distance. And I'm going to focus for just a moment on the very center of our solar system, the sun. Now, if you were traveling at the speed of light, it would take you roughly 8.5 minutes to get to the sun from Earth. So the sun's about 8.5 light minutes from us. There's a couple of different ways I like to think about that. One would be that if the sun just disappeared for some reason, we wouldn't know about it for 8.5 minutes. But don't worry, thankfully, there's no reason why the sun would just disappear. Another way I like to think of it is that if you were to walk outside right now, and if you were to look at the sun, don't do that. But if you were to look at the sun, again, don't do that. It's very bad for your eyes. But if you did, that's what the sun looked like 8.5 minutes ago, not what it looks like right now. So within these few light minutes of distance, we've got our smaller, rocky inner planets in our solar system. There's Mercury, Venus, Earth, and Mars. And you may notice there is a pretty sizable gap here in between Mars and the next planet, Jupiter. But that sizable gap is not totally empty space. There are thousands and thousands of objects in between Mars and Jupiter, but they're very small and they're not reflecting a lot of light from the sun, so it's really hard to see them. So I'm going to make them much brighter than normal so we can see them today. And that is the asteroid belt. So these are the asteroids that orbit in between Mars and Jupiter, some of the smaller rocky objects that we have in our solar system. And not all of the asteroids orbit in the asteroid belt in between Mars and Jupiter, but the vast majority do. And beyond the asteroid belt, we've got our gas giant planets, Jupiter and Saturn, and farther out still, what are often called the ice giants, Uranus and Neptune. And out here, we're to a few light hours of distance. We've already jumped up quite a bit in our distances in just a few minutes in the show here. So we started out by going a distance of 1.5 light seconds to get to the closest natural neighbor we have, the farthest that humans have traveled. It would be a few light minutes to get to the sun. Now out here by Neptune and also by my favorite dwarf planet, Pluto, we're up to a few light hours. So for example, if you were to travel across Pluto's orbit from one side of Pluto's orbit to the other, that would take you about 9 or so hours if you were traveling at the speed of light. And always when I get out to Pluto, I like to include a quick aside of why we don't call Pluto a planet anymore, because to this day, I get questions about that. Officially, Pluto has been called a dwarf planet since 2006, but still, I'll get lots of people asking, why isn't Pluto a planet? Did Pluto explode? Why do you hate Pluto? Is Pluto not in our solar system anymore? And I'm here to tell you, I don't hate Pluto. I really like Pluto a lot. I think it's very cool. And the main reason we don't call it a planet, we call it a dwarf planet, just has to do with where it is in our solar system. So we've got the asteroid belt. We also have an object or a group of objects called the Kuiper belt much farther out, which I'm going to show you the paths of. It's going to look kind of bright, come up kind of abruptly. There we go. So this is showing us where there are objects that are orbiting mostly outside of the orbit of Neptune. And you can see that a lot of them are in kind of this ring out near where Pluto is. This is what we call the Kuiper belt. And we did not know about the Kuiper belt and all these small, mostly icy objects until the late 90s and early 2000s as our telescopes started to get better. But once we did start finding them, we found several around the size of Pluto. So there was a conundrum. Do we add more planets? Do we change the definition of a planet? And one of the requirements that was decided on for a planet is it has to have cleared out its path, has to have a relatively cleared out orbit. Pluto goes right through the Kuiper belt, so it didn't fulfill that requirement, so it was changed to a dwarf planet. And now it's the biggest dwarf planet in our solar system that we know of. And just a few years ago, Pluto did have a wonderful honor that allowed us to learn a lot more about it, and that is that we sent a spacecraft out to Pluto to fly by really close and get us wonderful, beautiful close-up images of it. And along with that spacecraft, New Horizons, which went out to Pluto back in 2015, I've also put up the paths of the five farthest spacecraft that we have sent out so far. So these are showing us where Voyager 1 and 2, Pioneer 10 and 11, and New Horizons, where they have gone at this point. And the earliest of these, the Voyager spacecraft, they've been traveling since the 1970s. So they've been going for about 50 or so years by now. And they're traveling incredibly fast. But even so, all of these spacecraft, the farthest we've sent out so far, they haven't reached a distance that light could travel in a day yet. So we're still only out to some light hours at this point, not quite out to light days of distance. But we're not going to stop there. We have a long way to go still. So we're going to continue to zoom away from our solar system. And now we're in this interesting gray area of, are we still in the solar system or have we left the solar system behind? That's a little bit tricky to really define because there's a lot of things going around the sun. It's a little tricky to exactly define where does it end and where does it begin. But around here, now we're seeing the sun at its true brightness. Before I was dimming it down just a little bit so we could see the other things in our solar system more easily. But now we've switched our model of the sun so it looks how it would look if you really did fly out this far into space. And as I zoom away slowly, if you take a look around, you may notice we are starting to fly past some other stars. And the sun is starting to look like some of these other stars that we see in the sky. So once we're starting to fly past other stars, then I would say there's no argument whatsoever. We are outside of our solar system now, and we are flying among these other star systems in our galaxy. And if we want to check in with how far we've gone, we've jumped up in distance quite a bit already. So we've gone from those few light hours of distance, maybe a light day or so as we get past our farthest spacecraft. If we wanted to travel to the closest star to us outside of our solar system, that would take you about 4 years traveling at the speed of light. So we're up to a few light years of distance now. And I'm going to take us out to a few tens of light years of distance. And along the way, show you the locations of some very interesting objects that we have discovered over the last couple decades or so here. These blue circles that I've put up are showing us the location of stars that have exoplanets, planets that are outside of our solar system. And many of these stars have multiple exoplanets, just like our solar system has multiple planets too. And you can see there's quite a few circles here. We have found thousands of exoplanets so far, over 4,000 at this point. And we've only been finding them since about 1995, so not too long. And we're already up to thousands and thousands that we've discovered and mapped out where they are. And at this point, there is only one more time that we can check in with our human influence out in space, because as you saw, we have not sent any spacecraft out this far. So anything that we can observe out here is not because we sent something to this place to take a picture for us or whatever. It's the light of these objects that has traveled to us, gotten into our telescopes, and that's how we're able to learn where these things are. But there is one more thing that we have sent out into space, and I can show you where that is with this sphere here. This is what we call the radiosphere. Now, we have been sending radio signals that are strong enough to escape our planet since the 1930s, so a little around 90 or so years now. And all of those radio signals that escape our planet and go out into space, they're traveling at the speed of light. And unless they run into something out there, they're just going to keep on going at the same speed that they started out with. So the farthest that any of our radio signals could have gone is the edge of this little grid here, the radiosphere. But we're going to keep on going beyond this edge of our human influence out here in space. And we're going to continue to zoom away from the exoplanets that we have found so far and take a look at our galaxy. Now, I am going to put away the exoplanets, but I'm going to leave up the radiosphere, because I like to keep an eye on the radiosphere as we zoom away, see how long you can spot it as we go farther and farther. And my model that we're using in OpenSpace here of our galaxy is starting to kind of shift right now. So we were seeing before these individual stars, and where we've mapped out the closest individual stars we know of in our galaxy. The stars you will see if you go outside at night and you do some stargazing. But around here, the model has kind of shifted to include what we think our galaxy would look like if we could go out this far. So we have not been able to travel this far out into space yet, but we can see a lot of things in our galaxy. We can see some stars, we can see a lot of gas and dust, but we can't see our entire galaxy from where we are. So when we study other galaxies, and based on what we can see, we're able to construct a model like this, which is a pretty good idea of what we think our galaxy would look like, even though, unfortunately, so far, can't fly out there and take a picture. But I'll give you a second to look around the galaxy. Do you still see that radiosphere, that little teeny tiny dot? Near the top right up there? That's how far any of our human influence has gone so far, just that little teeny tiny area. Because now we're up to distances of thousands of light years. If you were traveling at the speed of light and you wanted to go across our Milky Way here that we're looking at, that would take you roughly 100,000 years. But even so, with the incredible size of our galaxy and its billions of stars, we think maybe a few 100 billion stars, it's just one galaxy. If we keep on going, we can see all these other dots showing up all around us now. And these dots are no longer individual stars. Every single one of these dots is another galaxy with its own billions or sometimes even trillions of stars. And if you're wondering about the colors of these dots, I'm sad to say that these are not the actual colors of these galaxies. I think that would be fun if it looked like cosmic Skittles out there in the universe. But no, we have color-coded these galaxies based on a variety of different things. Things like what data set is that galaxy part of? So what telescope was used to find it? Or what group of people found it? And also things like, is it part of a certain group or a certain cluster of galaxies? Sometimes we'll sort things that way as well. But this is an actual map. We've mapped out where these galaxies are relative to us as we observed them in our telescopes. And because of that, it's going to start to have kind of an odd shape because this is a map that is from our perspective of what we can see from here on Earth. And that means that it doesn't have everything that would be out there. So right around here, if I give us a good angle, you'll see that the galaxies seem to form kind of an odd shape. Looks sort of like a hourglass or maybe a butterfly or a bow tie. Some people say it looks like pasta. But I'm sad to say again, the universe is not shaped like a butterfly. I would like that too. But no, this shape is just because of, again, our perspective here on Earth. So as we gaze out into space, when we try to look in the directions that we're seeing on the top left and bottom right here, these large gaps that we're seeing, we do think that there are galaxies over there, but our galaxy is blocking our view. So our Milky Way galaxy we saw before has a lot of gas, it has a lot of dust, it has a lot of stars and all sorts of other things in it. And when we try to look over in those directions, our galaxy is blocking the view and we just can't see very well over in those directions. So there are even more galaxies than this, but this is just what we've been able to map out so far. And at this point, let's check in again about how far we've gone. So to get across our Milky Way galaxy would have taken us about 100,000 years if we were traveling at the speed of light. Out here, we're talking about a few billion years at this point. So we're a few billion light years away now. And something kind of fun about that is that we are also sort of time traveling in a way. Because this light, it takes so long to travel to us and get into our telescopes that by the time we see it, we're seeing these objects as they were in the past, not how they look right now. So if you recall back to near the beginning of the show, I mentioned how if you look at the sun, again, don't look at the sun, but if you looked at the sun, that's how the sun looked 8.5 minutes ago. Well, this is what our universe was like billions of years ago. And because of that, that means that there's only so far that we can go. There's only so far that we can see in our entire universe. And that edge of what we sometimes call our observable universe is all over the screen now. This is what we call the cosmic microwave background. So when you walk outside tonight, if it's a nice clear night out and you gaze up at the sky, you're not going to see this every single place you look. I'm grateful for that. That would scare me if I looked up and saw this. But if you could see this lower energy form of light in the microwave range of the light spectrum, so this specific kind of wavelengths of light out there that our eyes can't see, but our telescopes can, you would see this everywhere you look in the entire sky. So this is showing us just a few 100,000 years after when the Big Bang would have happened, when light was first able to just go out in all directions and expand all over the place. So I like to think of this as the baby picture of our universe, the earliest light that we can see. But since this is the earliest light that we can see, and like I said, as far as I can take you out into space, because we can't see beyond this, that means it's time to end our journey by heading on back home. And keep in mind, as we fly on back home, if we were really this far away out in space, and if we were really traveling at the speed of light, this journey would take us about 13.5 billion years. But thankfully, we're in the planetarium. It should only take us a couple minutes. And as we zoom back in, one last thing I do like to leave folks with is that all of this that we've been looking at, this isn't even everything we know to be in our universe. There's some really mysterious things out there, things like dark energy, some mysterious force that is causing space itself to accelerate as it expands. There's dark matter, some mysterious substance that seems to not interact with light at all, but we do see evidence of it at the edge of galaxies, especially in other places in our universe. And we call these things dark energy and dark matter because we're not really sure what exactly they are, but we do know that they make up about 96% of our universe. So all of this that we've been seeing is a teeny tiny portion of everything we know to be out there. And that can make folks feel kind of small and uncomfortable. And I agree, sometimes that makes me feel really weird. But I also like to think of it as, well, yes, we are this one teeny tiny dot in this gigantic universe, but look at all of this that we have found so far, almost entirely by just looking through telescopes. And there's a whole lot more to discover and a whole lot more to learn about. And that's pretty exciting. But even so, with that nice thought, I do always have a little bit of a relief when we get back to our human realm of the universe as we re-enter the radiosphere and have just a few tens of light years left to go to get home. In a moment, we'll see that closest star to us, the very center of our solar system, the sun. We'll dim it down a little bit as we re-enter our solar system. And as we fly past the farthest spacecraft that we have sent out, back inside of where the asteroid belt is, and back to the third planet from the sun, the only place in all of this that we have found life at all so far. It's also pretty incredible to think about. And with that, we are back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying around in space a bit with me, and I hope you all enjoy the rest of your day. Thank you so much for coming.